All right, good morning, everyone. So I'll mention first, I brought the exams home to grade, and then I sat there and I said to myself, it's my birthday weekend, so I just don't feel like doing this right now. So needless to say, I didn't grade everything. So hopefully I'll have it to you later this weekend. But another kind of story, my wife surprised me with a cake last night. And my daughter was chasing her around the house, trying to get the cake, going, party, party. And then as she was sitting there eating her cake, which she only ate the frosting, she was dancing while eating the frosting, screaming, party. It's like, God, I have a drunken sorority girl already on my hands. So anyways, that was my weekend. I just didn't feel like grading, so I'll have it to you later this week. Sorry about that, but sometimes these things happen. So anyways, I figured today what we'll do is take those inductors that we have been talking about before the exam, put those guys into circuits, just so we can talk about what they actually do in circuits. We're gonna look at 3 specific circuits, talk about these guys, and then Wednesday, we'll start all the stuff for the last portion of the exam. So we'll start looking at all the good stuff that gives us a light. We've already seen some of it, that's Faraday's law. But so let's talk about this. So the first thing we're gonna look at is what's known as an LC circuit. So we're gonna put here is a capacitor. And we're going to say that initially our capacitor at t is equal to 0 is fully charged. So there's some initial charge on these guys, and there's no currents running through the system. So the inductor is just basically sitting here at the moment. So let's first think about what's actually happening before we actually start applying Kirchhoff's loop rules and then find out what is actually happening. So what's going to happen is, as we mentioned kind of in class, is the presence of the inductor acts similar to a resistor, but one key factor between a resistor and an inductor is not present. And that's the fact that the inductor doesn't lose energy. So what happens is, as current starts flowing through here, there is a potential difference between the two sides, as we know, the back EMF. But it's not a resistor, so it's not going to radiate away energy. So energy is not going to be lost from the system, like a resistor does. So the presence here of the inductor is to make sure that current will flow, but it's going to make sure it flows in such a way that it doesn't lose energy. So it's not going to exponentially go to 0 over time. Okay? So what happened here is, if this thing is fully charged, this thing doesn't want to be fully charged. So what happened is the positive charges will want to move away from the positive plate, move around through the circuit to go then to the negative plate to cause both plates then to become chargeless. Right? So what happened then is, again, we pretend that positive charges are going to move. So I'm going to say that the positive charges are going to start moving through my wire. And as they start moving through the wire, current then is going to start to flow. So as these guys are going to start to move, what will happen then is, again, initially at time is equal to 0, this thing is fully charged, 0 current exists here. But as these positive charges start to move through my system, my current is going to go from 0 up to something non-zero, while the charge on here is going to get smaller and smaller over time. Until eventually what will happen is, this thing will have 0 charge, this thing will also have 0 charge, but I'm now going to have maximum current flowing through my system. Since I have maximum current flowing through my system, all these positive charges which are moving are now going to start to build up onto what used to be the negative plates, leaving the negative charges onto this plate, which means that this thing is going to eventually go to the point where I'm going to have it maximally charged again, but in the opposite orientation. So what happened is now this one's going to become the negative plate, this one's going to become the positive plate, at which time, when it reaches maximum charge, the current's going to stop flowing. It'll temporarily stop flowing until eventually it's going to repeat the process. So what will happen then is the positive charge is going to move around through this system in this direction, causing this one to decrease its negativity till 0, causing this one to decrease its positivity until 0, in which case the current again is maximum. So the current's going to continue to move in this direction, causing this to become positively charged again and this become negatively charged again. So we have something that starts off at an extreme, passes through equilibrium where it has maximum velocity, because remember velocity and current is the same, goes to the other extreme, momentarily stops and goes back to equilibrium and then back and forth, back and forth, back and forth. What did we call that at the beginning of this method? What kind of motion is that? That is harmonic oscillation, right? So this is exactly this thing. This thing is going to experience harmonic oscillation. So this is actually a harmonic oscillator, which we're going to actually show now. So what happened is, again, because no energy is lost in the system, all the energy remains in the system, but it's going to go back and forth between charge and current, charge and current, and charge and current. So let's see that. So let's apply Kirchhoff's loop rules. So remember, Kirchhoff's loop rule says that if we have a capacitor, and this is the positive side, this is the negative side, then potential difference going from A to B, so going across the capacitor from positive to negative, our potential difference then, delta V, is equal to negative Q divided by C. And for an inductor, we have the back EMF, which means for the inductor, in this case, if the current's going in this direction, so this is A, this is B, my inductor, then my potential difference across here is equal to negative L times di dt. So Kirchhoff's loop rule says that if we start off here at some point, so let's start off here in the quarter. So in this case, if I go around in this direction, so what'll happen then is what? I am going to get anyway, increase from here as well as an increase from here if I go in the same direction as the current. Otherwise, if I go in the opposite direction, but if I write this down, I get a negative Q over C minus then an L di dt is then equal to 0. Now remember though that I, by definition, is equal to the change in charge divided by the change in time, which means that this thing becomes then L times the second time derivative of the charge plus Q divided by C is equal to 0. Or finally, if we divide by L, we get the second time derivative of the charge plus 1 over LC times the charge is then equal to 0. So if we go back to what we actually talked about way back when, remember that if we had the second derivative of the position with respect to time plus the angular velocity squared times the position is then equal to 0 was our harmonic oscillator equation. So here we're just matching then that the charge is the same thing as the position, which means that 1 over LC is simply equal to the angular frequency squared. So this thing says that it does go through harmonic oscillation. It goes in harmonic oscillation in such a way that the charge as a function of time is then equal to cosine of omega t plus the phase factor, which in our case, the phase factor is simply equal to 0, where omega is equal to 1 over the square root of LC. So LC in this case is, or 1 over L squared of LC is our angular frequency. The current then is simply equal to the time rate of change of the charge, which is then equal to, in this case, minus omega times Q0 times sine of omega t plus the phase factor. We call that P sub 0. And this thing we usually then identify as minus I0 times sine of omega t plus the phase factor. Where I0 here then is equal to omega times Q0. So I0 is then what we call the peak amplitude then of the current. So this is then the peak amplitude, or just the amplitude of the current. So again, so basically what's happening is the system is going back and forth between who's storing the potential energy. When the charge on the capacitor is fully charged, in this case, then all the energy is stored in the capacitor by the fact that it has all the capacitance. So all the charge is stored on the capacitor. And then when it is 0 charge here, but all the current is flowing through the inductor, in that case, then all the energy is stored then in the current of the inductor. Anywhere in between, it's then a linear combination of simply the two of those. So let's talk about the energy stored then. So the energy storage So remember that the energy stored in a capacitor is equal to 1/2 the capacitance times the charge squared. And then the energy stored within inside of the inductor, which I'm going to call the magnetic energy, is equal to 1/2 the inductance times the current squared. So from this, what this says then is that's what? The energy is 1/2 the capacitance, C, times the charge. So this is Q0 squared times cosine squared of omega t plus phi0. And then for the inductor, this then is equal to 1/2 L times omega squared times the charge squared times sine squared of omega t plus phi0. Right. Now notice here, this prefactor is actually the same as this prefactor because of the definition of omega, which means that if I added these two things together, the total energy then is equal to the electric energy plus the magnetic energy, which is then simply equal to 1/2 the capacitance times the charge squared. Oh, sorry, I made a mistake. This is Q over C. That's why that didn't make any sense. Okay, so this is Q0 squared over C. Sorry, it's 1/2 C times V squared, which is equal to 1/2 Q squared over C. Sorry, I might see it in the wrong spot. Good. So I add these two together. So since these two factors, again, are the same, because remember that this is 1 over the square root of LC. So in this case, when I square it, the L's are going to cancel, which leaves the C on the bottom, which is the same prefactor as here. So if I add these guys together, the 1/2 are just simply going to come out. Cosine squared plus sine squared is equal to 1. So this means that the total energy then is simply a constant, which is given this way. So if I put an inductor into a simple circuit along with a capacitor, what happens again is that the energy is harmonically oscillating back and forth between the energy which is stored in the capacitor versus that which is stored within the inductor. So at any point in time, it's either going to be within inside of one or the other one, or a linear combination of the two. So this is the energy stored. So good. So let's do this, and let's use this to do an example. So this says I have a 1,200 picofarad capacitor. It's fully charged by a battery which has 500 volts. And it says it is disconnected from the battery supply and connected at t is equal to 0 to a 75 millihenry inductor. Determine A, the initial charge of the capacitor, B, the maximum current, C, the frequency in the period of oscillation, and then finally D, the total energy of our system. So let's put in these numbers. So here is my system. So here's my inductor connected to my capacitor. And I'm told here that my capacitance is equal to 1,200 picofarads, and my inductor is equal to 75 millihenry. And this thing starts off with a total charge Q0, which is equal to, so remember, this is equal to the capacitance times the potential. So Q is equal to CV. So in this case, for part A, I want to know what is the initial charge. Well, the initial charge then is equal to C times V, which is then equal to 1,200 picofarads, so that's 10 to the minus 12, times my potential, which is 500 volts. Was that part A or part B? Yeah, part A, good. So good. Looking at our numbers, find in this case then is that the initial amount of charge on my capacitor is equal to, this is 6 times 10 to the minus 7 coulombs, which is what? 0.6 microcoulombs. So this is my initial charge. Okay. So part B then says, what is the maximum amount of current? So the maximum amount of current is simply when I have I0, which we define then as equal to omega times Q0, which is then equal to Q0 divided by the square root of LC. So this is the maximum amount of current I'm going to have, which is when that sine is simply equal to 1. So this is then equal to 0.6 microcoulombs divided by the square root of 75 millihenry. So it's 75, 10 to the minus 3, times 1,200 times 12, 10 to the minus 12. Look at my numbers. What I get in this case then is that the maximum current is 63 milliamps. So this is my maximum current that's going to be flowing through my system. Part C then wants to know what is the frequency and the period. So what are these guys? Well, remember that angular frequency is related to regular frequency by simply 2 pi. So in this case, what we have then is that the frequency then is equal to the angular frequency divided by 2 pi, which is then equal to 1 over 2 pi times 1 over the square root of L times C. So plug in our numbers, we find in this case then is that our frequency turns out to be 17 kilohertz. So this is our frequency. The period then is simply equal to 1 over that. So my period then is equal to about 60 microseconds. So this is my period. Okay. Last part, part D, wants to know the total energy. Well, again, we know the total energy now is equal to 1/2 the initial charge squared divided by the capacitance. So, plug in those numbers. This works out to be 1.5 times 10 to the minus 4 joules, which is about 0.15 millijoules. So this is the total energy within my system. Okay. So not too bad. So these are LC circuits. Now another interesting circuit we can have is what's known as an LR circuit. So what's an LR circuit? So an LR circuit is one where we're going to take an inductor and add a resistor to it. Now here there's 2 different ways that we're going to do this. So one way is with a battery. And then the other way is just with the resistor and the inductor. So what I'm going to do here is I'm going to put in a switch. Okay, so let's say I have a switch, and my switch is going to be, let's say, here. So this is my switch. Okay. So basically what happened is I'm going to have the switch. So initially there's no current, there's no anything running through the system. I'm going to connect that to the battery. So I'm going to move the switch up. So that way the resistor and inductor are connected directly in series with the battery. We're going to let this thing then charge up until this thing becomes maximally charged. When it happens, then we're going to close our switch in the other direction. So that way the battery is no longer there. So the inductor will then discharge in this case. Okay? So this involves both charging and discharging. So let's look at charging first. So for charging, all we're going to do is we're going to close this switch here. So there's my closing my switch. So in this case, I have my EMF, which is supplying power to the system. I have my resistor, which is going to lose energy from the system. And then I'm going to have my inductor, which is going to supply a back EMF in this case, due to the fact that the current is going to run through it. So let's look at this case. So again, we're going to apply Kirchhoff's loop rules. So I'm going to go ahead and apply that at this part here. So I'm going to go across the battery from the negative terminal to the positive terminal, which means we get an increase in EMF. I'm then going to go across the resistor in the same direction as the current, because the current's going to go in this direction. So we know that manifests itself as a drop in potential of negative I times R. We're then going to go through the inductor in the same direction as the current, which means that's also a drop because of our back EMF of L times di dt. And all that has to be equal to 0. So this is our charging case. So good. So what I have here then is what? I have a differential with respect to time of the current here. I have the current on this side. So I'm going to bring that one term to the other side. So I'm going to rewrite this as E minus I times R is then equal to L times di dt. Now from here, we want to do then is bring everything with current on one side, everything with time on the other side by using our separation of variables. So I'm going to divide both sides by this guy, bring it over here, and multiply both sides by then the time, or at least the differential on time. So this is going to become di over E minus IR is then equal to L. Let's see here. Let's do it this way. dt over L. So here, I'm dividing this side over here, multiplying by the dt, and dividing by L. And now let's integrate both sides. So I'm going to integrate this guy from 0 to the maximum amount of current, so, or current at any time. I'm going to integrate this guy from 0 to t, which is the time at any point in time. From here, let's use a u substitution. So let's say u here is equal to E minus IR, so that du is equal to minus R times di, which means that di then is equal to negative du over R. That's my u substitution. Okay. So from here, I'm going to multiply both sides by the negative R. So let's rewrite this. So my integral now is going to become the integral of du over u is then equal to negative R over L, integral 0 to t dt. The left-hand side has different bounds. So here, when the current is equal to 0, u then is simply equal to E. And then when I is not equal to 0, it's going to be E minus IR. So my bounds of integration are now going to become, I'm going to integrate this from the EMF to the EMF minus the current times the resistance. The right-hand side is the easy part. This is actually minus R divided by L times T. That's the right-hand side. What's the left-hand side? What's the integral of du over u? Natural log of u. So this is going to become equal to the natural log of me minus R divided by E. So what we want is the current as a function of time. So I first have to get rid of a natural log. How do we get rid of a natural log? Do what? How do we get rid of a natural log? What's the inverse operation of natural log? E, exponential, right? So let's exponentiate both sides. So I get an E minus IR is equal to E times the exponential of minus RT over L. So finally, what I want, again, is I. So I'm going to add this term over here, subtract this term over here, and then factor out the E, and then divide by the R. So finally, I then is equal to E over R times 1 minus E to the minus RT divided by L, which we're going to define as E over R, 1 minus E to the minus T over tau, where tau is our time constant, which in this case, our time constant is L over R. So this is called our time constant. So we saw the time constant before when we looked at what? RC circuits. And in RC circuit, what we said was that when we were charging it, it took an exponential amount of time for this thing to actually charge. And it had a time constant of R times C, which basically dictated the amount of time it took for this thing to reach 66% of the overall charge. So this thing is basically saying the same thing. So what's going to happen is current is going to start flowing through the system. When that happens, I'm going to get a potential drop due to the resistor. The resistor is controlling then the current. This thing is also causing a back EMF, but once this thing fully reaches maximum charge, the back EMF then is going to go to 0 because the didt is going to go to 0, which means all the current is going to be dictated by simply that of the resistor, which is what this thing is saying. So what this thing says is that when time goes off to infinity, this term is going to go to 0, and then all the current looks like it's just running through a resistor. So the inductor acts like a straight wire at that point in time. There is no potential difference across it. But until that happens, the current through each one is not up to the maximum because it takes time for it to build up due to the presence of the inductor. And the inductor causes the back EMF, which causes the back current, trying to slow down the rate at which the current is flowing through, which is why it takes exponential amount of time for this thing to happen. So if I plotted the current versus time, this thing starts off with 0 current, and this thing is going to asymptote to the maximum amount of current, where the maximum amount of current is simply the EMF divided by the resistance. based off of Ohm's law. So this thing is going to quickly linearly increase, but then become an exponential and asymptote to that maximum current. That's what this thing is going to do. For discharging, it's basically going to do the same thing. So now if I close my switch, this thing now has maximum current running through it, which is simply that based off of the resistor. If I close it now, I get rid of the battery, what's going to happen then is all this current is now going to go to zero because I'm going to lose energy due to the resistor. So basically all the energy which is now stored within inside of the inductor will now get lost due to the presence of this resistor, which means that the current will eventually go to zero. Which means all the energy is also going to go to zero due to the thermal loss of energy because of the radiation given off by the resistor. So for discharging, we'll skip the derivation. So in this case, what we should find is that the current is then going to equal to whatever the initial current is, e to the minus t divided by tau, where tau is still simply equal to L over R. Still our time constant. Same exact time constant. So in this case, if I plotted the current versus time, this thing's going to start off at I0 and then exponentially decrease. Kind of horrible exponential, but there we go. As time goes to infinity. So this is my discharging, which is exactly the same process that we had for the RC circuit, for the same reason as before. Okay. So let's do an example of this. So this one says that at t is equal to 0, we have a 12-volt battery is connected to a 220 millihenry inductor in series and a resistor which has 30 ohms worth of resistance. So what I want to know then is what is the current at t is equal to 0? What is the time constant? What is the maximum current? How long does it take to reach half the maximum current? At this instant, what is the rate at which energy is being delivered by the battery? And then finally, at what rate is energy being stored in the inductor's magnetic field? So good. So let's talk about all these things. So good. So here we have a battery connected to a resistor, connected to an inductor. Here's my EMF, here's my resistor, here's my inductor. Look at the end numbers again. So battery is 12 volts, 30 ohms, and 220. So this was 12 volts, 30 ohms, and 220 millihenries. Okay. So part A. So at t is equal to 0, we know that there's no current flowing through the system because it was just connected to the battery, which means the current at t is equal to 0 is simply 0. Part B. What is the maximum current? Well, again, a maximum current occurs when the inductor starts acting just like a straight wire, meaning it's only carrying current through it. So all the current then is dictated by the resistor, which means that the maximum current then is just going to be the EMF divided by the resistance. So this is going to be our 12 volts divided by our 30 ohms. Look at our numbers. We got in this case then is that this works out to be, oh, I skipped part of it. Oh, that's fine. We'll do it backwards. 0.4 amps. There we go. I'm gonna call this part C, which it actually was part B. Wants to know what's the time constant? Well, we now know the time constant is simply the inductance divided by the resistance. So this is going to be 220 times 10 to the minus 3 divided by 30, which works out to be 7.3 milliseconds. So this is our time constant. Okay. Part D then wants to know how much time does it take for this thing to reach a current which is equal to 1/2 of the maximum current. So we want to know how much time does it take to reach half. So good, what do we know? So we now know that the current is equal to, in this case, the maximum current times 1 minus e to the minus t divided by tau. In this case, we want to know I is equal to half of the maximum. So we get 1/2 I max is equal to I max times 1 minus e to the minus t divided by tau, which means the I maxes are going to cancel. So this means e to the minus t divided by tau is equal to 1/2. Now, what I want is positive t, so I'm going to invert both of these two things. So finally what I get is e to the t divided by tau is equal to 2. What's the inverse operation of exponential? You guys just answered this question 5 minutes ago. A natural log, so it's natural log both sides. So this says that t divided by tau then is equal to the natural log of 2, which finally means that the time is going to be the time constant times the natural log of 2. So this is the time it's going to take for this thing to reach half of the maximum. So there's going to be 7.3 milliseconds times the natural log of 2. Plug in the numbers. Yeah, natural log of 2 is. I'm too old to remember these things. So this works out to be, once I find it, about 5 milliseconds. So this is the time it takes for this thing to reach half the maximum charge. Means okay? Part D then says, what is the rate at which power is given by the battery? Well, we know that the battery then is going to be equal to the power is the rate at which energy is given, in this case delivered by the battery. So it's going to be simply the current times then the EMF. Right? So in this case, it wants to know at that amount of time. So this is then going to be equal to half I max, because that's the amount of current running through the system, times the EMF delivered by the battery. So, longer numbers we find in this case then is, this is 2.4 watts. So this is the rate at which energy is being delivered by the battery. Part E then wants to know the rate at which energy is being stored inside of the inductor. So this is asking for power stored. So the rate at which energy is being stored. Remember, power is the rate at which energy is changing. Now, remember that the energy being stored inside the inductor is equal to 1/2 the inductance times the current squared. And remember, power is equal to the time rate of change of energy. So all I'm going to do here is I'm going to take that's UB, take its derivative. So I'm going to take the time derivative then of 1/2 the inductance times the current squared. Inductance is simply constant. Current is changing as a function of time. So this is going to be equal to then 1/2 the inductance times the time rate of change of the current squared. I'm going to take a derivative of that. I get a factor of 2 down. So this becomes L times I times di dt. Is okay with that? So now what? Well, we know that L times di dt is equal to E minus I times R. And I know that from Kirchhoff's loop rules. Because if I go all the way back to my Kirchhoff's loop rules, where is it? There it is. We had that E minus I times R minus L di dt was equal to 0, which means L times di dt, which is the back EMF, is simply equal to E minus I times R. So let's use that here. So that means that the power stored is then going to be equal to the current times E minus I times R. In this case, my current is simply half of the maximum. So it's going to be equal to 1/2 I max times E minus 1/2 I max times the resistance. Like my numbers, this works out to be about 1.2 watts. So this is the rate at which power is being stored inside of the inductor at that time when the current is equal to half of the time. Okay? Take a breath for people that are still writing. Okay? The last circuit we're going to look at is we're going to put all these things together. Let's look at the RLC circuits. So the RLC circuits, we're going to look at the most basic one, which is we're going to take a capacitor, which is fully charged at the initial time, connect that in series to a resistor, connected in series to an inductor, and this is our RLC circuits. So here, what we know is that what? At t is equal to 0, the charge on a capacitor is equal to the initial charge, whatever that maximum charge is. And we also know that the current flowing through our system is simply equal to 0. So let's say this side is positively charged, this side is then negatively charged. And again, what's going to happen is what? Current is going to start flowing through the system for the same reason it did with the LC circuits, which means that what? The positive charges here are going to start to move to the negative plates until eventually this thing is going to become what? 0 charge. This is also going to become 0 charged. But the presence of the resistor in this case, unlike the LC circuit, what's the resistor going to do? So if you think about our LC circuit, we said that that thing went through harmonic oscillation, right? Oscillated back and forth between energy being stored within inside the capacitor versus energy being stored within inside the inductor. But now, when I add in that resistor, what does the resistor do? So it has current flowing through it, and when it has current flowing through it, it does what? Does it get hot? Does it get cold? Does it stay the same? It gets hot, right? When it gets hot, it radiates away energy. So what the resistor is actually going to do is it's going to give off energy in the form of thermal energy. So it's going to lose energy from our system, which means that these two here are going to try to harmonically oscillate back and forth because that's what they do. While this one is going to say, I'm going to lose all that energy from you because I'm a douche. So the overall answer then is what? This system is going to be harmonic oscillation, but loss of energy, which is what we call a damped harmonic oscillator. So ultimately, the solution for this guy is going to be a damped harmonic oscillator because this portion is going to try to harmonically oscillate with him, but his job is to lose energy, which means ultimately this is going to be a damped harmonic oscillator. So let's see that. So again, let's use our Kirchhoff loop rule. So again, I'm going to start off here. From here, I'm going to go from the negative terminal to the positive terminal, which means we have an increase. So I'm going to get a Q over C. This one I have current going through it, and I'm going in the same direction. So that's going to give me a minus I times R. And then finally here, because current's going in the same direction, I'm going to get a minus L times di dt. But what's happening here is the charge is getting smaller here while the current is getting bigger, which means that what? The current is actually going to be equal to negative dq dt. And it's negative because, again, what's happening here is the charge starts off at maximum charge, but it's getting smaller over time. But as the charge is getting smaller, the current is getting bigger. So this derivative is negative. I need a negative here to make sure that this thing is positive. So all this is saying is that the charge is getting smaller, the current is getting bigger. That's what that negative sign there is for. So we use that in here, and then this thing becomes then, well, let's rewrite it. So I get an L times the second time derivative of the charge, plus the resistance times the first derivative of the charge, plus the charge divided by the capacitance is all equal to 0. If I divide everything by L, I get a second time derivative of the charge plus R over L times the first derivative of the charge plus 1 over LC times the charge is all equal to 0. So This is our damped harmonic oscillator. So what we see here is, here's our time constant. This is our frequency. So this is what we call the natural frequency. This thing is going to control the exponential portion. So this thing is going to be our damped harmonic oscillator. So again, all this thing is going to do is it's going to try to have current flow through the system, causing energy to move to here, and then back to here, and then back and forth. But again, the resistor is causing the energy to dissipate and go to zero over time. So overall, what's going to happen is it's going to depend on the size of each one of these quantities. So either this thing will show some harmonic oscillation before it goes to zero, or it will quickly go to zero, or it's going to go to zero even quicker. All those different damped harmonic oscillator cases that we talked about towards the beginning of the semester. So here we can't really write down a solution because it depends on the size of all of these quantities relative to each other. We'll leave it that way. But overall, what will happen is that the charge and the currents will both exponentially go to zero. So if I plot each one of these in respect to time, so if I plot the charge, my charge here is going to start off at whatever the maximum charge is, exponentially go to zero. And the current, in that case, will start off at zero in this case, and then increase, but then exponentially go to zero after that. So my current is going to go up, and then basically do something like this. Current goes up because initially the charge is moving around, so there has to be charge moving through. But as the charge goes to zero, the current also has to go to zero. Okay. So these are different circuits that we can create from inductors. So by adding these guys into circuits, the primary point of putting in an inductor, just like we did with the capacitor, was to store energy for later usage. This is the entire purpose of putting them in. But again, the effect of putting them in depends on the type of circuit of which it is I'm building. So we have the LC circuits, we have the LR circuits, and then the RLC circuits. Okay? So that's it from all the old stuff. So let me talk a little bit about chapter 31. So the next chapter we're going to start is chapter 31. So let's talk a little bit about chapter 31. Let's kind of build the stage, and now we're going to go further with on Wednesday. So up till this point in history, so we're talking about the late 1800s at this stage. The late 1800s. By the late 1800s, we knew multiple things. So the things that we knew were, we knew Gauss's law. So Gauss's law says that the closed loop or closed surface integral of the electric field was equal to the charge enclosed divided by epsilon naught. We know Gauss's law for magnetism, which says that the closed surface integral of B dot dA is simply equal to 0. We know Ampere's law, which says that what? The closed loop integral of the magnetic field integrated over the perimeter of some closed surface is equal to mu naught times the current which is enclosed. And we also knew Faraday's law, where Faraday's law says that the closed loop integral of the electric field dotted by or integrated along the differential length is equal to minus the time rate of change of the integral of the magnetic field dotted by the differential area. So these were some things that we knew going into the late 1800s. Other things we knew. We knew there was something generating light. So we knew there was light. But nobody knew what light was at this stage. They knew there was something called light. We knew we could see from light, but nobody knew the presence of light, where it actually came from. What else did we know? We also knew that the speed of light is equal to c, which is about 3 times 10 to the 8th meters per second. So we knew this as well. The reason that they knew this is because they took 2 poor souls, brought them up on top of mountains, had one mountain here, and then at a certain time, this person standing on top of this mountain had a light. So here's this light, it's carrying a light. And on a determine time, they would say, okay, I'm gonna flash my light. Okay? Somebody else was standing over on this side, watching, so they knew the distance between the two light sources. So they knew this, and say at midnight, so at 12 a.m., this guy was gonna flash light, and then he measured the time it took for him to actually see the light. So knowing the time it took for when this was flashed, when he actually saw the light, and the distance between the two, they knew that C did not travel at an infinite rate. It actually traveled at a finite rate, and it traveled at roughly 3 × 10⁸ meters per second. So these were the things that we knew going into the late 1800s. Okay? So we knew there was something called light. We knew its speed. We knew not Maxwell's equations yet, but we knew magnetism and electricity, where magnetism and electricity were considered still 2 separate things. Okay? Now comes somebody by the name of Maxwell, James Clerk Maxwell. Now what Maxwell did is he basically took these guys and he looked at them, and what he noticed was that what? These two things are completely symmetric, meaning that they say the same thing. What this one says is that electric field is generated by stationary charge, and this one says that a magnetic field would also be generated by a stationary magnetic charge if such a thing existed. This goes back to the whole non-magnetic monopoles that we talked about before. So since everything comes as a dipole, I can only have positive and negative charges simultaneously, which means that these two things say the same thing. But what you notice is that these two things do not. And what they say differently from each other is that what? This one says that a magnetic field is created by current, where this one says an electric field is created by a time-changing magnetic field. But what he started to think was, since these two things say the same thing, these two things should say the same thing as well. Which means that if this one says that a time-changing magnetic field generates an electric field, then this one is actually missing a term, which also should say that a magnetic field is generated from a time-changing electric field. So what Maxwell basically proposed was that Ampere's law was not complete, but that there should be some other term here, which was proportional to the time rate of change of the integral of the electric flux. This would then make these guys symmetric. They would say the same thing. So this one says that, again, electric fields are created by electric charge. This one says that if magnetic charges existed, this would create a magnetic field. So this one, by the fact that it's saying an electric field can be created by a time-changing magnetic field, this one should say something similar. So what he proposed was that this term here should be added to Ampere's law. What he also did is he went further, is he added this term in here and then basically showed that if you add this term in here, you can actually predict light. Light then was nothing more than an oscillating electric magnetic field where each one of those two are feeding off each other simultaneously in the form of a wave because of harmonic oscillation. And he went on to show that the speed at which it is traveling is equal to c, which is equal to 1 over the square root of mu naught times epsilon naught, which is equal to 3 × 10⁸ meters per second. So by adding in this extra term, you can actually predict light being actually physics that we actually understand, not some new form of physics. And you can actually find out exactly what the speed is from theory. This kind of caused an interesting point in time because up to this point, everybody in physics all basically did the same thing. There was no segregation between theorists and experimentalists like there is now. There were people that did everything. Like Faraday, he wrote down Faraday's law, but he actually did the experiments to actually come up with the Faraday's law. So the way it worked in the past was people would do experiments. From those experiments, they would then write down empirical laws and then use those to conjunction with each other. This was the first time ever that anybody had ever used theory first to predict something, and then somebody basically later showed it experimentally true. Hertz and other people actually showed that you can actually create electromagnetic radiation from electricity and magnetism. It wasn't Maxwell only theoretically predicted it. So this is actually when a rift started in physics. Some people became theorists, some people became experimentalists because of Maxwell. So basically, Maxwell went through and he actually predicted light. He predicted and showed it was actually electromagnetic radiation, and he predicted the speed at which it should be traveling, which maps experimentally what it should actually be doing. Now, this term here that he predicted actually makes a whole bunch of sense if you really think about it. And let's talk about why it makes sense, and then I'll call it a day. Let's think about a parallel plate capacitor. If we think about a parallel plate capacitor where I have current running through in this direction, and I have current running out of it in this direction, why does this work? So if we think about it, right? If this was a regular wire which was running through current, what happens if you take a pair of scissors and you cut that wire? Absolutely nothing. You kill your circuit, right? By cutting a piece of wire, you are creating a break in there, which means no current can actually jump from one side to the other side, because I can't have charges jump from this plate to this plate. But if we put a capacitor in there, even though we have empty air inside of here, there is no charge running from this plate to this plate because I have nothing jumping from this plate to this plate. It seems to work. I'm purposefully putting in a cut inside of my circuit, but it still works. Why? The answer is because I'm creating an electric field on the inside, but it's a time-dependent electric field. Because here I have charge building up slowly on top of these plates, which means I have charge building up slowly on top of these plates, which means I now have a time-dependent electric field on the inside. That time-dependent electric field acts exactly like a current. Hence, this. We've actually been seeing this since we started talking about capacitors. That we can actually create a current from the fact that we have a time-changing electric field. We'll pick up with here on Wednesday. I'll actually show where this comes from. This is what we call the displacement current. Acts just like a regular current, but it's a different creature all of itself. Okay? So, we'll see everybody on Wednesday. So don't forget, today is the last day of lab, so we're doing lenses today. And then after that, no lab next week. And then we will have a lab final, but that'll all be done being mostly simulations online. So we'll talk about that later. Yesterday was actually.